Our next keynote will be well known to any of you involved with science, with data, or who regularly attend its conferences. I'm very, very happy to introduce to you today Dr. Katy Huff.
Thank you. Thank you so much, Brandon, and the Python Software Foundation, and everyone for having me here today. For all of you for filling up every single one of those seats back there that were empty before I started. When I'm a little nervous or excited, I tend to kind of hold my breath. Does anyone do that? Yeah. So I haven't breathed in about a week. And I'm hoping that at the end of all of this, I will be able to breathe a little more comfortably. But generally speaking, I have had such a fun time in the last day and a half, and I really am looking forward to meeting every single one of you. I've met a bunch of you already. Little did you know that you would have to listen to me for 40 minutes, but now you know it. And you're all really, you're a gorgeous sight. I know you're all very brilliant, hardworking, curious individuals. And I'm here today to harness your power for my own devices. The Python Software Foundation, in inviting me, I've done the math. If I talk for 40 minutes and there are about 3,000 of you, the Python Software Foundation has given me 2,000 human hours to spend as I like. So thank you for sitting here. When I was given this invitation to give this talk, I could think of so many other Pythonistas who could give a really amazing talk to all of you. And the things that I can bring to you are very similar to what Jake brought yesterday. If you missed his talk, I'm so sorry. You really must see it. It was fabulous. Because I too am from scientific Python part of his mosaic. So my work, I'm a nuclear engineering professor at the University of Illinois in Urbana-Champaign. And my main contributions and involvement in the Python community is through SciPy. I help to organize the conference every year, more or less, and I spend a lot of time using those packages. And I also devote a lot of my time to the Hacker Within and other scientific computing education efforts, like the Software Carpentry Foundation, the Data Carpentry Foundation. These institutions are hoping to help scientists be better at using computers to make discoveries and to change our available lake of truth in the universe. And so software and data carpentry are really amazing institutions hoping to improve the reproducibility and ease of science with computers. I also, now recently am involved in a project called the Journal of Open Source Software. So JOSS is a really cool one-year-old experiment where we are reviewing research software in the same way that you might review a paper. We're doing it completely in the open on GitHub. We're giving research scientists some credit for the software that they develop towards their science. And it's a really fun project. I'll talk a little bit more about it. So a lot of my work is related to improving the lot of scientific computing researchers. I spent a little time in the last few years at the Berkeley Institute for Data Science, and in that time, I was grateful to be able to waste my academic hours on writing a book with my friend and colleague Anthony Skopatz on effective computation in physics, and writing a couple chapters in a book called The Practice of Reproducible Research. Of course, these books are closely related to the kind of things I've just described in these foundations, okay? And now I'm at the University of Illinois. I am very lucky and proud to be involved in the National Center for Supercomputing Applications, which is responsible for some of the greatest supercomputing capabilities on a university campus in the world. And with NCSA and the Department of Nuclear, Plasma, and Radiological Engineering, I'm a professor who leads my own research group. And my work is focused on advanced nuclear reactors and fuel cycles. So what I'm interested in is improving the way that nuclear energy is produced. And in order to do that, my tool of choice is, you guessed it, Python. But also a little C++, a little Fortran here and there. You know, I'm a scientist. I do what I can. But generally speaking, I'd like to bring you today into my world of doing science with computers. And I'd like to keep you there forever, just a little bit, okay? So why am I a nuclear engineer? You know, I had breakfast with one of you yesterday, and when you discovered what it is I do, I said, yeah, I'm a nuclear engineer. He said, wow, you don't hear that every day. And he doesn't, but I do, actually. But it's true. So nuclear engineering isn't really very common. But we have a very big impact on the world. And that's why I'm a nuclear engineer. I started out much like Jake, actually. I was an astrophysics, cosmology interested undergraduate at the University of Chicago, doing some of those sky surveys related to the cosmic microwave background. And I took a look around, and I said to myself, what are the problems in the world? Am I impacting them at all? And I looked and I saw that a large fraction of the world doesn't have good access to energy. And it was obvious to me that fossil fuels are a short-sighted and damaging way to produce energy. And renewables are great, but nuclear actually produces so much more energy per land area. And in fact, it's one of the lowest mortality sources of energy in the world. Save geothermal nuclear energy is responsible for fewer deaths per terawatt than any other form of energy. Save geothermal. So I thought, I'm curious. I love physics. You know, I was a physics major at the time. And I want to be immortal. So the only real way that, so I'm an atheist. And what that means is that I genuinely believe that this is my only chance at life. And I too will eventually die. And it'll be sooner, probably, than I'm ready. And in that time, I would like to make an impact on the world that the world has to keep because it's so useful. So I'd like to be a positive change in the world. And for me, as a young physics major, it became obvious that my impact should be nuclear energy. So I went to grad school, got a PhD, whatnot, like you do. Oh no, this is the Wi-Fi failing. Let's see if I have this beautiful thing. Oh, phew. So I wanted to impact the world with a little bit of fission. And most scientists are driven in this way. We're an extremely optimistic bunch of people. And generally speaking, we're very hopeful and optimistic that science could, completely alter the state of play in humanity. Scientists are very, very optimistic people who expect that this pursuit of truth will genuinely impact the world around them in a serious fashion. And more important, so we basically imagine that science is just this unending box of possible discoveries to improve our universe, to know more, to discover truth. And but more important than our optimism, actually, is our pessimism. So science is based entirely on well-structured skepticism. All right, so here in 1895, about 120-something years ago, scientist Lord Kelvin, responsible for the temperature scale, he thought heavier-than-air flying machines are impossible, because he was a steadfast scientist who believes nothing until it's been proven. But all of you sit here having just used the ubiquitous flight that humans have achieved in that time. Not long, in fact, really, in the human time scale after he said this, we were flying around. And that's what builds science, is this grumpy, deep skepticism. And indeed, it's an organized type of skepticism. R.K. Merton in 1942 described this as being critical, and it says, all ideas in science have to be tested, subjected to rigorous, structured community scrutiny. Structured community scrutiny, right? The theme of this whole sort of conference, the universe of Python here, is community, and scientists have been relying on it for a long time. And indeed, another way to put this is that central to the scientific method is that we believe that everything is full of error. There are errors that we introduce accidentally. There are errors that we introduce without, realizing that there could be a source of that error. And the scientist's time and effort, if they're doing it right, should be expended rooting out error all the time. Okay. And it's a difficult effort, but the main enemy is ourselves. So Richard Feynman described this as an utter honesty. It's no small, normal level of honesty where you're just trying to be truthful, but rather this bending over backwards of honesty where you seek out the roots of error that you might not have thought of before you ever claim to know something. So a scientist should spend most of his time trying not to fool himself. So I'm telling you all this to give you an idea of how important it is that science be reviewed by the community that is capable of assessing its merits. Here's Richard Feynman, actually. So let's take a little brief foray into history, actually. So Richard Feynman's this lovely character in the middle. And around him are Stanislaw Ulam and not Enrico Fermi. And John von Neumann. So John von Neumann's on the left here. And Stanislaw Ulam is on the far right. And Richard Feynman's in the middle. And of course, they're together in Los Alamos to build the A-bomb, right? How many of you use a Monte Carlo type algorithm in your work? Yeah, raise your hands. Yeah, that's a lot of hands. So basically, conversations like this in Los Alamos were responsible for the Monte Carlo algorithm, okay? Because Monte Carlo is the ideal way to represent neutron diffusion. And they, of course, were building a bomb, unfortunately. But science drove this small piece of math, which now drives an enormous swath of the analysis in the world. This Monte Carlo algorithm, class of algorithms, it's based on sampling probabilities. It's really good for integrating, and it's good for coupling many parameter systems. And ultimately, it's really, really good for neutron diffusion. All right? The behavior of neutrons in a reactor, in a bomb, anywhere, all right? In any kind of multiplying medium. And frankly, it is central to computing, all right? Because it was actually the first algorithm that John von Neumann programmed into his general processing computer, the ENIAC, the very first of the kind of more modern type of computer that could accept any program, programmed more generally, so you could put in the algorithm without physically changing the machine. And so John von Neumann, though he was involved in this Manhattan project, said, I'm thinking about something much more important than bombs. I'm thinking about computers. So this is actually like an interesting little foray just because it ties together computing, my field, nuclear engineering, and how their work and my work, and indeed many of your work, descended from these few moments of science. And science is in a kind of complicated way right now. How many of you were involved in the March for Science recently? Yeah, a lot of you. Yeah, pretty cool. Because a lot of you are scientists, right? How many of you have a science degree of some kind? Yeah, no kidding, right? Like, I'm really preaching to the choir, but not all of you are still doing that science, that domain science that you were trained for. You know, your domain science had the opportunity to give you the kind of like critical, curious, excited possibility of programming. You know, and you're all, many of you, very much the better for it. And, you know, like I said, you know, science, it's trying to build and organize knowledge and test explanations about the universe. It's trying to do it in a systematic, objective way that's transparent and reproducible. And it can't do that without the support of, you know, our government, without the support of its community, et cetera. And it's really not science otherwise. Jake said yesterday, he talked about the reproducibility crisis in science. And in fact, you know, he is extremely hopeful that the computation that, you know, we're really verging on, IPython notebooks and everything, will make it so much easier to be reproducible, and we'll eventually have this reproducibility crisis behind us. And I really, really hope he's right, because there are all these ways in which, you know, non-reproducible results sneak their way into journals these days. Some of them are unintentional, mistaken statistics, you know, bits of error that we didn't expect. But some of it's not unintentional. There are fake journals. There are fake papers. A colleague in front of mine at the Berkeley Institute for Data Science is also a writer for Science Magazine, Science the Journal, right? But in the magazine portion. And he was responsible for submitting a fake paper about how chocolate can help you lose weight and getting it accepted and everything. And he effectively is like trolling the journal universe in order to identify its weak points. And we need community members like that, constantly skeptical. Lord Kelvin's out there in the community, you know, being skeptical of the science around us. You know, and science relies on peer review. And so the increased amount of open science in the universe, code on GitHub, you know, all of these things increase the ability for you to be able to see the science and be skeptical, for me to be able to look at my colleagues' science and be skeptical of it. You know, and science relies on that transparency. It also relies on attribution. So getting credit for the software is really important. Right now, academic scientists don't get a lot of credit for the software they write, and we're trying to change that with this Journal of Open Source Science. It relies a lot on collaboration, right? John von Neumann and Stanislaw Umlaum, and they probably wouldn't have come up with Monte Carlo without talking to each other at Los Alamos. But it also relies on impact. Without sort of like a tree falling in the forest, you know, without anyone using it, has any science really been done? Without it turning into a technology that you can use, has any science really advanced? You know, since the sort of Pythagorean era, science has been perfecting these kinds of ideas. And in the brief time that it's existed, open source software is now better at all of them. All right? So that's why, yeah. And that's why I'm talking to you, okay? Because I think the computers should do exactly what Jake is suggesting. They should make it much easier for us to be reproducible. No scientist now has an excuse for not double-checking and producing their data and putting it with the journal article that they make claims in. But scientists aren't actually trained to use computers very effectively. And we need you to help us. How can you do that? Well, so a long time ago, 3rd century Confucian philosopher said, "Tell me and I forget, show me and I'll remember, but involve me and I will understand." So I would like to involve you. Yesterday, someone's found this poll. So everyone, please get out your Pokemon Go machines, and try going to this URL up at the top. And I'd like to ask you, I think there are various changes that the world needs to see. I think we have challenges like water. I think we have challenges like energy. Someone's listed climate change. So here you can now, humanity itself is a challenge facing humanity. You can add points to a certain poll entry. You can add poll entries. So it should just bump itself up. Misinformation, artificial intelligence is something that could help. That's right. There is an education gap. So, what moves you? A little trolling. Python 2, that's right. Woo! So, oh no, Poll Everywhere promised me that 1,000 people would be able to log into this today. Fail. It says poll is full, but it's actually still accepting responses, so I don't know. All right, well, we'll move on. I'm sorry if you didn't get to participate. It looks like at least a couple hundred of you are involved. All right, so I think one of the key challenges is water, right? Let's imagine that you think clean water is a huge problem for humanity. How many of you agree with that? Yeah, awesome. Cool. So all of you are an extremely specialized group of people with a skill that can be better than just liking something on Facebook, right? You have skills that can directly impact our ability to keep water clean for the world, okay? There is a United States Environmental Protection Agency. Some of you may believe that the EPA should be better funded. Perhaps you could give them a gift in kind. They have a tool for water network resilience. It calculates how networks of water transport contaminants and, for example, poison people if they're drinking it. It's written in Python. GitHub.com, US EPA, WNTR, it has 12 contributors. It probably has some open issues. Last I checked, it actually didn't, so maybe they're tracking tickets somewhere else. There's also an open global glacier model. One of the largest sources of fresh water in the world is existing glaciers. We don't want them to melt into the ocean, and we don't want them to melt at all. So it's important to keep track of their thickness, which this model does. You can see glacier thickness over here on the side, and different sections. You can see glacier altitude and whatnot. And this tool, this global glacier model, is on GitHub. Has 43 open issues. Get after it. Climate, right? Let's say you were worried about the climate. There's this beautiful planet visualization that I love. It's by this Null School Earth world. This Cambeck Earth has 30 open issues. It's not Python, but I really like it. If you like JavaScript, go nuts. Atmospheric science is Python, automated climate data analysis and management, Python package for atmospheric sciences. You're interested in the climate, you want to help analyze it, you can contribute. They have some really beautiful stuff, matplotlib plots of this is a precipitation total across the world based on a model that they've done, and it breaks the precipitation out into its different components. We won't go into the science of it, but it's very important for people to be able to assess the source of this kind of precipitation. 54 open issues on GitHub in Python. There's a Department of Energy project called PyArt, and it too tracks some of the precipitation. This is like attenuation is a way that we measure precipitation. And this Python ARM radar toolkit, also known as PyArt, is a data model-driven interactive toolkit for working with weather radar data, and it contributes to climate analysis. 52 open issues. Right? You're getting the idea. Energy. All right, so this is me. This is what I care about. This is what's driving my entire life, right? Nuclear power is 20% of your electricity. It's 60% of the United States emissions-free electricity. So if you care about getting rid of carbon, nuclear is a pretty good way to do it. I, as a graduate student, wrote a simulation framework, sort of like SimCity for the nuclear industry, to track materials so that we can assess ways to recycle nuclear spent fuel. All right? Assessing those strategies is key to making them policy. So Cyclist is pretty cool. It's written in mostly C++, but there's a ton of Python in it, and a ton of Python, and a ton of generator code written by Anthony Skopats. And this is the nuclear fuel cycle. It basically tracks when you dig fuel out of the ground, and then you pass it through a reactor, and then maybe you either recycle it or you bury it. We do this with agent-based systems analysis by giving it a communication framework and allowing physicists to add physics. Any particular facility is a black box that might create material or accept material. It might do both. You connect them all, and you get a really interesting, complicated simulation, and you can actually track specific spent fuel casks through the world. Cyclist is able to ask questions around, what would happen if we changed our reactor type in the United States, and we went from our current light water reactor design to a sodium-cooled fast reactor design, for example. And we're able to analyze those transitions. We're able to analyze what kind of material goes through, what kind of masses. And we have 62 open issues. Go for it. I also contribute to Pine, which is Python for nuclear engineering. It allows us to do all kinds of cool stuff that nuclear engineers need to do. This is a recent analysis from my graduate student, Andrei Ryklevsky, from 3 days ago. And it tracks the composition evolution through a molten salt type breeder reactor that we're analyzing if you recycle some of the material. Pine has 90 open issues. Okay. So you can also, there's also some great visualization out there. Pine uses YT to visualize some of its results, but YT is in that middle layer. It's not a domain-specific tool so much as a visualization tool in Python that's specifically for a number of different kinds of volumetric data analysis. And so you can use it in lots of different fields. We use it in Pine. This is a neutron diffusion simulation. This is a gorgeous star formation simulation. And YT has 91 open issues. It's pure Python, beautiful, beautiful stuff. But in addition to just energy and some astrophysics, YT is capable of addressing some health questions. Here's a volumetric rendering of a human CT scan that was made possible by YT. Super beautiful. And so if you want to contribute to these kind of beautiful visualizations used across fields, you could do that. In health, there's also a really cool project called Pulse to Percept for people who've had some corneal problem. They can have a corneal implant someday that can mimic vision by sending electrical impulses into their eye for retinal prosthetics. And I don't know much about biology, but there's a group of people who have set out to solve this sort of mathematical problem of signal processing in the eye for these retinal prosthetics at the University of Washington eScience Institute. And it's all Python. And it has these beautiful sort of visualizations of where you would put the electrodes in the eye. That's the ocular disc, that black hole, and those dots are where you would put the electrodes. Pretty cool. And it has 4 open issues, even though it's brand spanking new. There's also various neuroscience projects. NiPi has 27 open issues. MNE has 181 open issues. You're getting the idea. There are also just tools that are super cool. One of my favorites is Pint, which helps scientists deal with units. It allows you to just turn normal numbers into numbers with units. It has 97 open issues. All right, so those are some projects I just wanted to highlight. Jake told you about some phenomenal astronomy projects yesterday. Amazing stuff, world-changing, at least someday. If you want to impact the world today, if you too want to be immortal, you can give me your brain, give these people your brain. I did not develop most of these codes, just the nuclear engineering ones have I been involved in. There's so much out there that you can directly contribute to. They have bugs they don't understand. They most scientists have not moved from Python 2.7 to 2.3 yet. Help us. And in fact, if you don't want to do that, you could also help JOS review papers. The Journal of Open Source Science, or Open Source Software, has this great GitHub interface for reviewing code and assessing its contribution just according to a very short paper. So most of the work is in the code review. So I'll leave you with this. There are 4 simple steps to immortality. Be curious. Pick a cool project. Contribute to it. And save the world. I have a bunch of people in the Python universe that I would not be here without. Some of you are in this room. I thank you, mostly the Jupyter team and the BIDS team and people related to the scientific Python universe. Thank you. And that's it. I don't think I have time for questions. Thank you. There's no time for questions right now.
Thank you very much, Dr. Huff. Thank you for to our earlier speakers as well. We're at time, so there'll be no questions. Come up and talk if you want to share with them and thank them. Let's give them another big round of applause. Have a good day.